Hello everyone, welcome back to the online classes by Konnur institutions. In the last class, we were discussing about the vapor pressure and vapor pressure of a liquid solution. In case of vapor pressure, I will remind you in 5 minutes what we taught in last class. What is the meaning of the vapor pressure? Vapor pressure means the pressure exerted by the vapor of a liquid at equilibrium, that is known as a vapor pressure. Vapor pressure is directly proportional to temperature. If the temperature is increases, vapor pressure is also increases, and vapor pressure of a solution always less than 1 atm, 1 atmospheric pressure, and volatility is directly proportional to vapor pressure. If the liquid having a weak intermolecular force of attraction, so that will easily evaporate, it means more vapor will come, so those vapor will exert a pressure, it means more vapor pressure will be exerted. And one more point you can remember regarding the vapor pressure, very important, vapor pressure is inversely proportional to the boiling point. So the solution having a less boiling point having a more vapor pressure. And also we were discussing about the vapor pressure of a liquid solution. Among that, both the solute and the solvent are taken a volatile liquids. Those are volatile. If you have taken a pure solvent, volatile one component, those solution is a solvent is evaporate to form a vapor molecules. Those vapor molecules will exert a pressure on the solution. That vapor pressure is denoted by the P1 naught. P1 naught in the sense what? Naught indicates that pure vapor pressure or vapor pressure of the pure component. And another volatile component same, allowed to evaporate, those vapor molecules are collected over the solution. Those vapor molecules will exert a pressure on the solution surface. That pressure is called as a vapor pressure, that is denoted by the P2 naught. So naught indicates a pure vapor pressure. If those volatile liquids, when we add to the one beaker, we will get the solution. So if you want the total vapor pressure of that solution, we need to do the sum of the partial pressure of the two components or components present in the solution. That is a P total is equal to P1 plus P2. So we already expressed the mathematical form of Rod's law also. So we explained the Rod's law statements also. Partial vapor pressure of each component is directly proportional to the mole fraction of the solution. That is a Rod's law. According to that, P total is equal to what we got. So that is a P1 naught plus into bracket P2 naught minus P1 naught into x2. So and also we were discussing graphical representation between the mole fraction and the vapor pressure of the two components. So in the last class, this much we will discuss. We were discussing. And today's class we will discuss about the problems on the Rod's law. That is, we written a problem here. Vapor pressure of chloroform, molecular formula of chloroform is CHCl3, and dichloromethane, molecular formula is CH2Cl2 at 298 Kelvin are 200 mmHg and 415 mmHg respectively. It means 200 mmHg chloroform and 415 mmHg dichloromethane. Question is, calculate the vapor pressure of the solution. Calculate the vapor pressure of the solution. It means what? We have to calculate the total vapor pressure of the solution, that is a P total according to the Dalton's law. If you want the total vapor pressure of the solution, sum of the partial pressure of the components present in the solution. So calculate the vapor pressure of a solution prepared by mixing 25.5 gram of CHCl3 chloroform and 40 gram of CH2Cl2 at 298 Kelvin. And second question is, calculate the mole fraction of each component in vapor phase. This is the very important. Vapor phase means Y1, Y2 we have to calculate. So now we will go to the solution. First one, what it is? Calculate the vapor pressure of a solution. What you have to calculate? What they given, first we have to write this. Vapor pressure of chloroform and dichloromethane they had given. So that is denoted by the vapor pressure of a pure component is denoted by P1 naught. That is P1 naught is equal to 200 mmHg. 200 mmHg. And one more is P2 naught is equal to 415 mmHg. They had given this one. And we have to calculate the vapor pressure of the solution. That is P total is equal to question mark. Yes, we have to calculate the P total, that is the total pressure of the solution. Here CHCl3 is taken as a first component, CH2Cl2 is taken as a second component. So now what is the mathematical formula of the Rod's law? That is P total is equal to P1 naught plus P2 naught minus P1 naught into X2. This is the formula as we already discussed in the last class. So P1 naught is the pure vapor pressure of the first component, P2 naught is the pure vapor pressure of the second component. They had given already P1 naught they had given 200, P2 naught they had given a 415. We have to calculate the X2 here. Mole fraction we have to calculate. So what is the mole fraction of X2 is equal to? X2 is equal to N2 divided by N1 plus N2. We already know the mole fraction formula. Now number of moles of second component, number of moles of first component. So number of moles of second component is equal to weight of that divided by molar mass, and N1 is equal to weight divided by molar mass. This is the formula as we already know that. So now N2 is equal to second component. Here second component is CH2Cl2. How much they had given? Weight of that. So that is 25.5 gram is CHCl3 and 40 gram is CH2Cl2. Second component is CH2Cl2. They had given a 40 gram. So that is weight of that second component is 40 gram divided by molar mass of CH2Cl2 divided by molar mass of CH2Cl2. So dichloromethane. How many carbon are there? 1 carbon. So 1 into 12 plus 2 into 1 hydrogen and 2 chlorine atoms. 2 into 35.5. Molecular formula of CH2Cl2. This is 85. Now it is molecular formula of the second component is 85. 40 divided by 85, 0.470. There is no unit for the mole fraction. This is N2. And N1 is equal to weight of the first component CHCl3. How much they had given? 25.5 gram. That is 25.5 gram divided by molar mass of CHCl3, chloroform. 1 carbon atom will be there. 1 into 12 plus 1 into 1 plus 3 into 35.5. This is the molecular mass of CHCl3, that is 119.5. Molar mass of first component is 119.5. 25 divided by 11.9 is equal to 0.213. We get the mole fraction of the number of moles of N1 is equal to 0.213. X2 is equal to, how much we getting? X2 is equal to N2 divided by N1 plus N2. N2 already calculated here. N2 is equal to 0.470 divided by 0.213 plus 0.470. That is X2 is equal to 0.470 divided by 0.213 plus 0.470 is equal to 0.688. This is the mole fraction of the second component. So now we can fill the value of X2 here. That is P1 already we know that 200, P1 naught 200 plus P2 naught they had given how much? 415 minus P1 naught 200 into X2 value already calculated here 0.688 0.688. Now it is 200 plus 415 minus 200, that is 215 into 0.688. Now it is, we have to multiply these two and we will get the final value. P total is equal to 347 point. So we have to multiply this one. 347.9 they had given in mmHg, that is mmHg. So this is what P total. First one already calculated. Calculate the vapor pressure of the solution prepared by mixing of 25.5 gram of CHCl3 and 40 gram of CH2Cl2. The total vapor pressure of the solution is 347.9 mmHg. Now second one. So we'll move towards the second one. Yes. Second one is calculate the mole fraction of each component in vapor phase. This is what X2 is equal to mole fraction of second component in a solution we already calculated. X1 is equal to, we have to calculate that one also. Those are the mole fraction in solution. We have to calculate the mole fraction in vapor phase. Mole fraction in vapor phase, that is Y1 and Y2 we have to calculate. Y1 and Y2. So now Y1 is the what? Y1 is mole fraction of component 1 in vapor phase, and Y2 is the mole fraction of component 2 in vapor phase. According to the Dalton's law of partial pressure, according to Dalton's law, formula of this one is, that is P1 partial vapor pressure is equal to Y1 into P total. This is the formula to calculate the mole fraction in vapor phase. Same, P2 is equal to Y2 into P total. So we have to calculate the Y1. Y1 is equal to P1 divided by P total. Y1 is equal to P1 divided by P total. So now Y1 is equal to, P1 is nothing but partial vapor pressure. How to write this one? P1 is equal to P1 naught into X1. They didn't given a P1 partial vapor pressure, they didn't given. They had given a pure vapor pressure and mole fraction. So using that we can calculate the partial vapor pressure of this P1. P1 is equal to P1 naught into X1. Fill here. Now it is P1 naught into X1 divided by P total. Y1 is equal to P1 naught into X1 divided by P total. P1 naught they had given already, pure vapor pressure 200 mmHg. X1 we have to calculate. P total we already calculated here. So already calculated X2. Using this one we can calculate the X1. X1 is equal to 1 minus X2, that is 1 minus 0.688 is equal to 0.312. This is the mole fraction in solutions. X2 and X1 are the mole fraction of first component, second component in solution. Now we have to calculate the mole fraction in the vapor phase. That is the P1 naught is equal to 200 they had given. X1 we already calculated, that is 0.312 divided by P total is equal to how much? 347.9. That is 347.9. If you divide this one, Y1 is equal to, we'll get that is 0.179. This is approximately 0.18. This is Y1, mole fraction in the vapor phase. And next one, P2 is equal to Y2 into P total. We want Y2 vapor phase. Y2 is equal to P2 divided by P total. Now P2 is equal to, P2 is what? Partial vapor pressure. They didn't given. Using that, P2 is equal to P2 naught into X2. Using this formula, we can calculate the P2. That is P2 is equal to P2 naught into X2 divided by P total. Now it is P2 naught they had given. That is 415 mmHg. 415 into X2 already calculated 0.688. 0.688 divided by P total is equal to 347.9. 347.9. If we divide this one, it will get the 0.82. This is Y2 is equal to 0.82. Mole fraction doesn't have any unit. This is the mole fraction of first component and second component in vapor phase, and you have to remember the thing here, X1 and X2 are the mole fraction in the solution, Y1 and Y2 are the mole fraction of the in the vapor phase. So this is the calculation of mole fraction of each component in the vapor phase and also vapor pressure of the solution. Yes sir, now we will discuss about the Rod's law for the solution containing non-volatile solute or vapor pressure of a solid in liquid solution. In yesterday class we discussed about the vapor pressure of liquid solution. In such cases the solute and the solvent are taken as a volatile nature. Both are volatile in nature. Here the Rod's law for the solution containing non-volatile solute or solid in liquid. As we already know that, so that is when solute is added to the solvent, solution is formed. Here the solute is a solid and solvent is a liquid. Solute, what about the nature of the solute? This is volatile. Solid, it is volatile solid. Sorry, this is non-volatile. This is volatile. Non-volatile solute means what? Solid is non-volatile, that will not evaporate, or that solute will not form the vapor molecules. That is a non-volatile added to the volatile liquid. What about the vapor pressure? Now we will discuss that. So let us consider the example. The solution is allowed to evaporate in a closed vessel. Yes, I have taken a solution here, liquid. When this solution allowed to evaporate, so the molecules present at the surface will have a tendency to escape from the liquid surface to the vapor. So these having a more tendency to escape liquid to the vapor phase. When this solution allowed to evaporate, these molecules will form the vapor. These vapor molecules are collected over the solution. As the evaporation is increases, vapor molecules over the solution is also increases. Those vapor molecules will collide each other, and also those molecules will hit to the surface of the wall of the container, and those molecules, when they strike on the surface of the liquid, they exert some pressure on the solution. That pressure is known as a vapor pressure. That pressure is known as a vapor pressure, as we already discussed in the last class. I have taken a pure solvent here, hence we have to P1 naught. P1 naught in the sense what? Vapor pressure of pure component. Vapor pressure of pure component. So now, when we add the non-volatile solute to such kind of a solvent. It means volatile solvent. So when we add the non-volatile solute to the solvent, non-volatile solute. So this contains what? Non-volatile solute, and volatile liquid, volatile solvent. Yes. When we add the non-volatile solute to the volatile solvent, some of the solute particles will replaces the solvent particles in the surface. Example, you can take these are the solute particles. Yes. Here the sum of the solute particle replaces the solvent particles. At the surface now number of solute particles are also there and number of solvent particles are also there. Here in case of a pure solvent, these are all solvent particles. Those will escape to form the more vapor, and more vapor means a more number of vapor will exert a more pressure. Hence we will get the more pressure for the pure solvent, that is P0. When we add the non-volatile solute to the solvent, the escaping tendency of a solvent particle is decreases because of the solute particles are present at the surface. So here the total number of solute particles are less. These will evaporate to form the less number of vapor molecules. These less number of vapor molecules will exert a less pressure on the solution. So that pressure is denoted by the what? P1. That pressure is denoted by the P1, partial vapor pressure. Here the total vapor pressure of the solution is less than the pure solvent because of the non-volatile solute will accumulate on the surface of the liquid. Because of that reason, total vapor pressure of the pure solvent is more than the P1. Why? Because it is because of the non-volatile solute. This solute will not evaporate, only the solvent particles will evaporate. Number of solvent particles are less number of solvent particles will form the less number of vapor molecules. Those less number of vapor molecules will exert a less pressure, hence we will get the total pressure will be less than the pure solvent. This is the vapor pressure of a solid in liquid, or Rod's law for the solid solution containing non-volatile solute. Vapor pressure of the non-volatile solute containing solution is directly proportional to the mole fraction of that one. So that is the vapor pressure of the solid in liquid. Yes. Vapor pressure of a solution containing non-volatile solute is directly proportional to the mole fraction of the solvent. What it means? If the volatile solvent is present, means a number of moles are expressed in a mole fraction. It means it will be evaporate to form the vapor molecules. Those will exert the pressure. This mole fraction is directly proportional to this vapor pressure. That is the meaning here. Vapor pressure of solution containing non-volatile solute is directly proportional to the mole fraction of the solvent. Now it is. So partial vapor pressure P1 is directly proportional to X1. P1 is equal to P1 naught into X1. Here P1 is the partial vapor pressure. P1 is the partial vapor pressure and P1 naught is the vapor pressure of the pure component. X1 is the mole fraction of that component. So this is the vapor pressure of solid in liquid. Now we'll discuss about the Rod's law as a special case of Henry's law. Rod's law as a special case of Henry's law. In case of Henry's law, that is the partial vapor pressure of the gas is above the solution is directly proportional to the mole fraction, that we can write according to the Henry's law. Henry's law. Partial vapor pressure of gas is directly proportional to the mole fraction of that gas in the solution. That is P1 is equal to Kh into X1. And according to the Rod's law, that is partial vapor pressure of the component is directly proportional to the mole fraction of that solution. That is P1 is equal to P1 naught into X1. Rod's law as a special case of Henry's law. When it will become equal? When the value of P1 naught and Kh is equal. When Kh value equal to P1 naught, in such cases P1 is equal to X1, P1 is equal to X1. This is the Rod's law as a special case of Henry's law. Now we'll discuss about the lowering of vapor pressure. Lowering of vapor pressure. Yes, lowering of vapor pressure, that is LVP. Lowering in the sense decreases. Why the vapor pressure of the solution containing non-volatile is decreases? Because of the presence of non-volatile solute, the total vapor pressure is decreases. That decrease is directly proportional to the solute dissolved in the solution. One more point you can remember. So now, if you want the difference in the vapor pressure of pure solvent and solution, it is. That is P1 naught is more than P1, and if you higher vapor pressure minus lower vapor pressure will get the what? Delta P, change in pressure, change in vapor pressure. That we can write that. So delta P is equal to P1 naught minus P1. How to define the lowering vapor pressure of the solution? That is the difference between the vapor pressure of the pure component to the vapor pressure of the solution. So that is a delta P of the lowering vapor pressure. How to define this one? Difference between the vapor pressure of pure solvent and that of solution, is known as lowering of vapor pressure. Vapor pressure will be decreases because of the non-volatile solute present in the solution. That we are writing that delta P is equal to P1 naught into P1. So now we will discuss about the relative lowering vapor pressure. Relative lowering vapor pressure. Shortcut we will call as relative lowering vapor pressure. So relative lowering vapor pressure means it is the ratio between the lowering vapor pressure of the solution to the vapor pressure of the pure solvent. So what is the lowering vapor pressure? That is P1 naught minus P1. This is the lowering vapor pressure. It is a ratio between the lowering vapor pressure of the solution to the vapor pressure of pure solvent. This is called as relative lowering vapor pressure. How to define this one? It is ratio between lowering vapor pressure of solution to the vapor pressure of pure component. So that is called as relative lowering vapor pressure. So these formulas will help you calculate the relative lowering vapor pressure or vapor pressure of the solution in numericals. Remember that. We will discuss remaining part of the solution in next class. Thank you.